Good morning, everyone. Can you hear me well? Yeah, okay. So today we have the pleasure of listening to a very interesting talk, is what I think about, by Professor Julio Navarro. I mean, it's very difficult to introduce him because he's a very famous person. And if no Navarro Frank and White profile for dark matter, well, Navarro is him. And he's professor at the University of Victoria in Canada, and did a lot of seminal work in the study of the structure of dark matter halos in the Lambda CDM cosmology. So today, well, then he did many other things about on galaxy evolution, and today he goes to the limit of galaxy evolution, I think, with his talk. So the smallest galaxies that can form in our universe. So Julio will be here today and tomorrow if you want to talk to him. And hopefully next year we'll be coming for a much longer visit. So there will be more room for discussion and more room for collaboration with him. And I'll let Julio.
Thanks a lot, Claudio. Of course, it's a pleasure to be here. It's not my first time here. If I remember correctly, I've been here a few times. But it's always a pleasure to come to your little island of paradise here in the middle of the Atlantic Ocean. Because you can be scared when you look at the map and you say there's that and there's nothing else, just water around it. But anyway, enjoy your paradise here. I also come from an island and live in an island in Vancouver Island in Canada. So this is, and I'm actually now on sabbatical in the British Isles. So islands are for me, basically. All right, let's, I'll tell you a little bit about this, reading the small print, basically looking at the smallest scale structures in the universe and trying to make sense of them in the sense of, or in the cosmological context of dark matter, the nature of dark matter. Let me start with a few obligatory, context slides. I think Those of you who don't work on this field will probably benefit from this. And the idea is that here by looking at the cosmic microwave background that you see over here, these are the temperature fluctuations in the microwave background over the whole sky, and looking also at the large scale structure, these are redshift surveys here, we've been able to construct what we call the standard model of cosmology. At least today, at present time, we have a universe that is made of basically 5% or so of things that we understand, like matter, like things you touch here, this wood, this our bodies, the sun, stars, etc. And the rest is basically things that we don't know, but we can label. We've got things that gravitate, we call that dark matter. It turns out the majority of the matter content of the universe today, and something called dark energy, which we know even less what it is, but we know it has some kind of, or we need it to explain the expansion rates of the universe today and how it's changed over sometimes. Okay, so you say, well, basically, this is basically almost a statement of ignorance, more a statement of fact or knowledge, but we can get a bit more and understand a bit more about this by looking now at the details. So let's look at this. You look at this map, you get the impression that this is kind of a Gaussian field of some sort. Since there are fluctuations that are not particularly overly related in different senses. And this is the initial conditions of all the structures of worlds that we see today. This is what the universe was like a thousand times ago. No, how to say, when the universe was 1,000 times smaller than today. I was with an old friend yesterday. No, sorry, a few days ago in Madrid. And he said, yeah, 3 wives ago, I remember that happened. I said, what? Since when are we counting things in the numbers of wives? We're way too old. And they said, okay, now then there was a student. The student said, oh yeah, no, he came 3 Ramon y Cajals before you. What? So now we count that our time is the numbers of Ramon y Cajal that is elapsed between one and the other. Anyway, we choose our units of time, clearly. Anyway, this is a Gaussian process of some sort. It gives you the idea, okay? So we'll try to characterize this Gaussian field of fluctuations, how it changes in time, and what we can learn about it. Of course, we can measure that Gaussian field, whatever that is, at redshift 1,000, as I told you, in the microwave background. We can look at it also in the more local universe, closer to us, present the universe, by doing redshift surveys. And the way we tend to characterize this, if it's a Gaussian, then all we need to know is the variance, okay? Mean is 0, can always shift it to 0, and then we need the Gaussian. The Gaussian has all the information you need. Okay? So let's start characterizing Gaussian. Of course, when we say Gaussian field and characterize this variance or dispersion, however we're going to call it, then we need to specify scale. And the trick, of course, here is that the universe appears to have a well-defined relation between the variance and the scale. The bigger the scale, the smaller the variance is. Okay? And in a particular way, in ways we can actually measure. And the interesting thing about doing this in a microwave background, for example, is that the fluctuations are tiny. They appear very big in this thing that I showed you here, but they actually have been hugely amplified. You know, it's 1 in a million in terms of matter fluctuations that have been amplified so they can actually see them. Otherwise, it would just be exactly uniform. So they are really tiny. It means that tiny, it means that they're in the linear regime. So we can actually make a lot of progress by looking just at micro background. Look at micro background, you're looking at very large scales, basically, scales of a degree or so or bigger. On the sky, you translate them into scales. The scales correspond to a typical mass, if you want, inside a scale of the orders of 10 to the 20, 10 to the 21 solar masses. This is, of course, basically mass of the horizon. All the masses have the Hubble radius or fractions thereof. But you can see the fluctuations are kind of like a power law. And that power law actually was predicted long before this was observed by theorists who were saying, well, what can we, if we are given, freedom without data, to explore what kind of fluctuations we can have in the early universe, what would I have? He said, well, first of all, let's make it a power law, because if it's not a power law, we need to introduce a scale. Okay, so power law, we have the exponent, right, and nothing else. Okay, fine, a power law. And what is the slope of the power law? And if you choose the slopes that are not a particular value, 1 in some units and in some definitions, the fluctuations diverge, either a small or a large scale. So there's one solution for which the fluctuations don't diverge, neither at small or at large scales. Why don't they diverge? Because they're constant. Basically, fluctuations are those, we call this the scale invariant spectrum. You probably have heard about this 1,000 times or read about the scale invariant. That means that all the fluctuations in the early universe had the same amplitude in the gravitational potential. Everything had the same escape velocity, all the fluctuations, regardless of the scale. The prediction from that is that, of course, all the velocities of a particular system of different masses should be the same. This is the same escape velocity, same velocity, characteristic velocity. We know that's not the case. The sun moves at 200 kilometers per second around the Milky Way. In a dwarf galaxy, stars move relative to each other at, say, 10, 20 kilometers per second. In a galaxy cluster, galaxies move relative to each other at, 1,000 kilometers per second. So clearly that's not the case. Why is that not the case? What has introduced this scale in the problem? And what's introduced this scale in the problem is the fact that I showed you before, the balance between energy, matter, etc. That balance today, which I showed you in that pie, changes with time. And that governs how these fluctuations grow at different times. And because of this change in the importance, for example, of baryons and energy, etc., you imprint a particular shape to this power spectrum, as we call it now. This is the baryons here as a function of scale. This is the baryons, this is the power spectrum, and then it bends over. And now we have all these observations that are different redshifts, they're being corrected to a particular time, etc. Details for what I'm telling you here. We can actually fit this with a very, very simple model where basically the dark matter is a collisionless cold particle. It means that clusters on all scales, and that the universe is dominated today by something like the cosmological constant. With that, we can make a prediction for what this shape should be. And the only parameter left is the normalization, which normalized by looking, say, at one point, a point in the macro background, doesn't matter where, and that's it. And this is the fit, with minimal number of parameters. And you must agree that is stunning. This is actually one of the biggest, and I don't think I'm over-exaggerating, one of the greatest intellectual achievements of the past, few decades. Understanding this, the origin, the structure, and the evolution of all the structures in the universe. And this prediction is what we call the prediction from Lambda Cold Dark Matter. You see, it's pretty good. It's over 10 decades in mass here. That's a lot. Okay, most theories in physics work over a couple of decades. So, and they're considered hugely important, whatever. This is actually of that order. So the most interesting thing is that this theory makes predictions. If you want to say, well, it's been fitted to match here, and this also, fair enough, and there's, of course, some inputs or observational constraints here, but there are predictions. For example, if it's cold dark matter, as I want to use as a usual theory, then you predict that this fluctuations will exist on all scales because, it's cold, there's no particular scale introduced by the velocity of the particle, and therefore you expect the dark matter to cluster or to have structures on all scales. And extrapolate this curve all the way over there down to the, Earth mass or whatever, okay? In ways that we can actually do the calculation. And do the calculation has another advantage, which is that we can simulate this. So if it's cold, it's collisionless. The only interaction we care about is the gravity, and therefore, and I expand the universe. We'll put this in a computer, and I've been involved in doing this for many years now. And I think this is a fairly mature field now, where if we put these particular initial conditions characterized by the Gaussian field that I told you before, and we evolve this in time, we have this prediction. What should the structure look like? A map now of the structure of the universe. And it looks like this. It has this honeycomb structure on very, very large scales, like, this cosmic web, as we call it. And then as you go towards regions which are more highly overdense, you see that dark matter kind of collapses onto itself. The universe is expanding, it's like creating these funny structures from just nothing, from Gaussian field and gravity, you create all these little holes and things. But in some regions, because the overdensities are large enough, the dark matter becomes bound to its own structure, and it has enough time to turn around and collapse into itself. Those are regions of the universe where the densities are high enough that the crossing time is shorter than the age of the universe. And those regions achieve something close to virial equilibrium. And this is what we call dark matter halos. Okay, so if you dig, you zoom in, you end up with these systems. And this is really a prediction. There's nothing like it we would have predicted just from observations. You see the dark matter halos has a particular center, it has all this little bunch of substructures, as we call it. And that's because it forms through mergers of smaller objects, many of which still remain orbiting around. And so these predictions are actually important. These halos are, of course, very important. This is the basic nonlinear structure, the basic brick of foundational structures in the universe. And it has several properties in cold dark matter that we can exploit, we will exploit. One of them is what we call the self-similar nature. They look alike. This is one 10 to the 15 solar masses. We measure masses inside a radius where the time it takes to go around is the age of the universe. I would call that the virial radius, whatever reason that is. But you can use it to compare a small or low mass halo with a big mass halo, and once we scale them to the same characteristic virial radius, they look the same. And they all look the same. Every halo is kind of a copy of each other, statistically speaking, a copy of each other, just made it bigger and more massive, or smaller and less massive. So that's actually quite interesting. It means we can understand one halo and we understand them all. And the other thing we know is, we've been doing this for quite a while now, we know how to count them, right? So we know how many halos there are per unit mass per unit volume. Okay? We also know how they cluster, if I have one here, how many have around, etc. So lots of things we actually know about this, and they're used for all the predictions that you see. When you see these DESI things, all that, those are being used. All these results, in one way or another, are being used. And we also know the internal structure. Okay, this is what I'll tell you a little bit about. The internal structure basically is, you take the halo like this, you find the center, it's easy. It's in the middle here, the densest part, and you say, well, how does the density of dark matter drop when you go from the center, densest region, out? Plot this, and I plot this in a log-log plot, and you see something like this. A funny curve. This is log in radius, log density. It's not as power law. It's something that curves over. It curves over in a particular way, so it'll be important for in a few minutes. But it's, as I say, it's always the same. All halos look like this. Once I scale them, to the same, to a particular size and characteristic density, they all look the same. And it has this interesting property that if you go towards the center, the density always grows. There's a particular law, it doesn't matter, but it grows. It means that if I go closer to the center, it's always denser and denser and denser. Okay? We call this a cuspy halo. And it has, it's a real signature prediction of cold dark matter. This historical value, I'll show you this. This is the NFW profile, as Claudio was saying. This is the same formula as before, same curve as before, for 4 different halos of different masses. And the idea is, if you take this one, low mass, and you shift it down and to the right, you match exactly this one, which is the galaxy cluster. That is the self-similar nature of cold dark matter. I told you we know also about the numbers. We can count them as a function of mass per unit volume. And this is the curve that comes out of proper mass here, count here, the unit volume, and it looks a curve like this black line here. And say, well, okay, what is going on with these halos? But the halos to us are the sites of galaxy formation. Baryons, this minority of the matter and the universe that is made of the things that make up stars and stuff, or galaxies, fall into the potential wells of this dark matter, which is dominant. And then in regions, in halos where it can emit radiation, it cools, goes to the center, and it falls all the way to the center, gets denser and denser until it starts forming stars, and we form what we call galaxies. So basically, every time you see a galaxy in this zeroth order description, you see a dark matter halo. And of course, you can count galaxies. Well, I've become pretty good at this. We can count galaxies as a function of mass as well. Because the mass we measure in a galaxy is the stellar mass or some surrogates of it. And we can plot it here in this plot, the same. We can count how many galaxies there are per unit volume as a function of stellar mass now. That's the curve you see over here. You see the curves don't have the same shape. Okay? They're different. This seems more like power law that goes up and up and up. This kind of seems much flatter, seems to cut off a lot more truncate a lot more sharply. And all those things, are interesting. There are thousands, hundreds of thousands of papers written on these things. And just let me tell you, we're still introducing here, the topic here is, what we do with this. They're not the same. Therefore, what can I do, right? How can I assign a galaxy to a halo? People say, well, a massive galaxy, usually we should go with a massive halo, so it has more stuff. The more is more, right? So, well, and you notice, look, if I take, say, 10 to the 12 solar mass galaxies in stars, there are X number of them, and I compare this with this halo, so 10 to the 14, whatever, I have the same numbers. So what if I do the following? I just put these galaxies in these halos, these galaxies in these halos. I match them horizontally, okay? I'm guaranteed almost to get the right result, right? I'll get the right number of galaxies, but provided that I make an assumption. What is the typical stellar mass per halo mass? And that is what we call the stellar mass-halo mass relation. Details don't matter too much, but it becomes interesting for the purposes of what I'm interested in now is in the faint end. Okay? When we go to the faint end here, 10 to the 9, 10 to the 8, 10 to the 7, this thing is much flatter than this one. Imagine, just to have a mental trick here, a visual impression, imagine this was exactly flat. What would this prediction mean? It means if we take, say, 10 to the 9 solar masses here, 10 to the 9 solar masses, will this work? Yes. Fine. I think I broke this thing already. 10 to the 9 solar masses, I match them, I get some halo mass, 10 to the 8, the same halo mass, 10 to the 7, the same halo mass. I always get the same halo mass. All right, a little bit more, so it's not exactly flat. But it means that basically when you go to the regime of faint dwarf galaxies, all dwarf galaxies, regardless of their stellar mass, are sampling, statistically on average, the same halo, the halo of the same mass, the characteristic mass, the threshold mass, below which you cannot form galaxies, because you form galaxies in halos that are a lot less massive than that, you have way too many galaxies that you don't observe. So that's a simple trick. By looking at this thing, we already tell there is a threshold mass, halo mass, to form a galaxy. And we can actually see this visually in simulations. It actually comes out naturally if you want. This is the structure of something like the local group, Milky Way and 31, plus satellites in dark matter, and this is what it looks like in stars. You can see there are a lot fewer clumps in stars than there are in dark matter. So a lot of the halos that we simulate are dark. Okay? And that is actually what we're going to be talking about today. And what I'll tell you in the next time, and the time that I have left, hopefully I have some left, I'll tell you about two things. One is the faintest galaxy that we know in the universe, which was discovered by Simon here, or a student who is visiting you for a few months, visiting Giuseppina, of course. And then I will tell you about another galaxy, which is fainter than the faintest galaxy in the universe, okay, if that is possible, because that's in a nutshell what I'll tell you about. Hopefully I'll have time for that. Let me put some words and some numbers into it. This is from a simulation now. The stellar mass here on the left, blue, look at the blue curve, and halo mass. And you see the relation that I'm going to tell you. So massive things are massive galaxies and massive halos, and then as you approach, the lower mass, you have this vertical thing, this kind of cutoff. Below 10 to the 9 and a bit, there are no stars. Okay? Things become dark. Okay? So that's a strong prediction, right? We should be able to test this prediction. Okay, so let's see how we test this prediction. All right, first of all, the prediction, they all have the same mass, all right? That's interesting. Let's see if we can actually do this. We can take a galaxy 10 to the 6, 10 to the 5, 10 to the 4, 10 to the 3, etc. All have the same halo. I mean, you cannot rule this out. It's crazy. We're not doing our job properly. Let's look at these galaxies now. What do the galaxies that 10 to the 6 and below look like in the local universe? They look like this. This is, of course, an example. It's bigger than 10 to the 6. It doesn't matter. This is the 4 next dwarf spheroidal. A good friend of Giuseppina, if I remember correctly, worked on this a while ago, and many others. Actually, Giuseppina is, of course, one of the pioneers of working on these things. And this is what it looks like. I mean, they're close to us, they're faint, so we can only see them very close to us. They're close to us, and therefore we can actually resolve them into stars, individual stars. So I have a bunch of stars, and I can measure lots of things, star formation history, stuff that Karma here do, of course. But also for the purposes of what we're interested in two things. We can count them. We have characteristic size, so size that contains half of the stars, and we can measure velocities, line of sight velocities, the radial velocities for individual stars, for many of them. We have two numbers, right? Measure velocities, supposed to be a mean velocity for all the velocities. The mean velocity is just the recession or approach velocity of the galaxy, and the dispersion is what we're interested in. We take the dispersion, we square it, we multiply by the radius, and it gives us a mass. That mass is a very characteristic mass of this system, and it's a very well-defined number. Square the velocity dispersion times the radius. It's a very well-defined number. It means the mass inside that circle, okay? With a constant, whatever. But I know the mass inside that circle. If I know the mass inside that circle, then I know the mean density inside the circle. So it's just mass. I know the mass. I know this radius, divide m over r cubed, and there are pi's that never get right, but you get the density. And now let's look at what we can do with this. The dark matter here is dominant. The stars are actually not very important for the potential, and therefore they're just tracing the potential. So you have two galaxies, the dwarf, and one is smaller than the other, and they live in the same halo, and the halo's cuspy. The smaller galaxy should be denser than the big galaxy, right? Simple. Okay, well, that's what we can do, all right? But before we go there, I'll tell you what also this Fornax, for example, has elicited a lot of attention in the field of dark matter. Historically, I'm so old. I talk about papers of 1979 or something that's crazy. Anyway, but this is the kind of thing that people do. Okay, let's look at Fornax. Okay, I told you we can measure a mass very well, all right? But we'll say, well, if you measure mass very well inside that radius, we'll measure mass inside some other radius. Then you have to do trickery. So you have to say, well, I'll choose some stars and not the others, etc. Okay, the whole thing becomes a little, as we say in Argentina, la cancha se embarra. I don't know if you understand that. It means the playing field becomes muddy. Okay, so it becomes more complicated, right? But it can be done, and hats off to the people who try these things. We're going to measure masses inside two radii. Say this is, instead of mass, I'm plotting velocity, just m over r, similar thing, but two radii. Okay, let me see if I passes my slides. And there's these two yellow points here. Compared with the predictions of these cuspy halos, you see the yellow point in the center seem to be lower than what you expect. It seems to be less dark matter than what you expect. People say, whoa, wait, that means that it's not cuspy. That means it's not cold dark matter. And then you say, well, have you looked at the error bars, first of all? But, people get excited. People like to do lots of things that are very exciting, especially when they're young. I used to do things like that. Now it's become so conservative. Oh my God, it's absolutely terrible. Absolutely terrible. But anyway, so less dark matter in the center, not cuspy. What does that mean? And they say, well, is there any other galaxy that looks like this? There are other galaxies that look like this, but for example, this one here, there's again a rotation curve, as we call it, a prediction of cold dark matter, this gray thing, and the shape of this particular rotation curve. They say, well, there's less dark matter in the center. Here, there is something here. We need to explain why this is, and we're going to change dark matter. We're going to do something to this cold or to the collision part of the dark matter to make these things. Unfortunately, it becomes a bit more complicated because when you look at rotation curves in detail, these are four galaxies, the same stellar luminosity, same rotation velocities, different rotation curves. You see some have this deficit of dark matter here, some don't have any deficit at all, red with what you expect, and some have actually an under deficit, or what is called the super average or something, whatever, some number like that. So it's not completely clear, and this is sometimes goes by the name of cusp versus core problems. Many may have read about those things. We tried to change the name for it just to attract some publicity, and we called it the rotation curve diversity problem in a paper a few years ago. Little we knew that diversity has been banned now. So if I went to give this talk at MIT a few months ago, and I call it the rotation curve problem. So, because otherwise you could be detained and sent to Guantanamo or whatever it is the people say in the US. Scientists these days, poor souls, Anyway, now it's called the rotation curve problem, okay? Anyways, so how can we do this? Like a couple of things you can do to fix this problem if you believe that there is a problem. One is to make sense and to make use of this collisionless part of dark matter. See, because it's cold and collisionless, you have this profile that I showed you before. The interesting thing about that profile is that it curves over like that in density, it curves over in velocity as well. Look at here in the black, you see the velocity dispersion. It goes up and down, okay? It goes up and down. It means that it's colder in the center than it is in the outer parts, or at least in the middle parts. That means if you change this collisionless, so instead of particles never seeing each other except for gravitational interactions, they actually now have collisional cross-sections that can actually bounce one from another. And just assume this is an elastic collision. Over time, in regions that are high density, where collisions are very frequent, they will start exchanging energy. And exchanging energy in such ways so as to achieve equipartition. So velocity dispersion will go from the black to the blue. We'll get the same velocity dispersion in the center where collisions are frequent, and it will change the density profile. Instead of a cusp, see at the top here, in the black, you get this core. You reduce dark matter, you push dark matter out by redistributing energy. Okay? So that's interesting. It goes by the name of self-interacting dark matter, and people have played a lot of tricks about this. There was a conference in Valencia a few months ago on this. I went to give a talk there. As soon as I said self-interacting dark matter at the IFIC was some institute, the light went out. So hopefully this won't be the case today. So to protect us from, we're so far in the Atlantic that basically the trolls are not finding us. Anyway, another way of doing this is by saying, well, what if this cold dark matter, what's the cold dark matter? This standard, WIMP, as people call it, say, well, so a particle like, like a neutrino, but no neutrino that has 100 GeV mass, whatever that means, okay? I said, well, what if we make that mass very, very small? Instead of 100 GeV or 10 GeV or 90 GeV, let's make that really small. Let's make that 10 to the minus 22 EV. So we change up 600 decades in mass. When you make this so small, the particle is so light that its de Broglie scale wavelength becomes of the scale of a kiloparsec. So if you want to, another way of saying this is like saying, well, now if you have a de Broglie wavelength that's so big, then you have, something akin to degeneracy pressure, right, on small scales. And the dark matter cannot cluster as much. It has to have a ceiling of density it can reach. Yeah, and you can actually work out that ceiling through simulations where you combine Poisson's equation with Schrödinger's equation, and you end up with a prediction. The density of dark matter that you see in a halo, for example, is whatever, some number. So it's 10 to the 7 or something, so mass of kiloparsec cube, if the mass is 10 to the minus 22. And if it's minus 10 to the minus 21 or 10 to the minus 23, you get different results. And you say, well, what do I need to fix the Fornax problem? You see, it's 10 to the 7 or so. Remember that number, 10 to the 7 solar masses per, doesn't matter exactly the units, but it's 10 to the 7. And it's the same here. Look at the numbers over there, 10 to the 7. All these models have been motivated to fix things like Fornax, like this, the dwarf spheroidals in some sense. Okay, good. So now we have a test, right? So if it's true that halos are cuspy and I play my game of putting different galaxies, different sizes, as I reduce the size of a galaxy, I should get denser and denser objects. And if it's not, they should get always the same density because they all have, remember, it's all the same halos, right? So they all have the same density and should get the same density. There's a strong prediction. Low mass galaxies, especially when I go to the very faint end, they should all have the same density if it's not cold dark matter, or higher densities if it's cold dark matter. And this is the vertex. This is observational. So we can actually take all the satellites of the Milky Way, then 31, everything else they can find that is reasonably low mass, and you plot them here, and they do what I tell you. You have the size of the galaxy, and the mean density. And this is what you get. Blue are the faintest objects of the galaxy, or satellites of the galaxy we know. We call them the ultra-faint galaxies. And you can see that in general, as the galaxy gets smaller and also less massive, it becomes actually denser. Right? So immediately you say, those models, at least the way they were conceived to explain Fornax, SIDM, they're just wrong. but not wrong. They don't match the observations. Of course, one can revise this, say, well, no, the cross-section is changing with velocity and it becomes bigger and smaller. Interesting, very interesting things, okay? But it's not what you were designing to say. You wanted to have low density, and now you have high density, okay? And the numbers are big. They're not 10 to the 7. You know, the densest objects we find are 10 to the 9 or something. Okay? Big numbers, hundreds. It's not a factor 2 effect. What we really want is a smaller galaxy. We want a galaxy that's of the order of 1 parsec, because they don't have a prediction. What is the density of that object? A few times 10 to the 10. That's huge. That's the same density as you see in, you know, in the cores of a globular cluster. People like Kalman know like globular clusters. So it's so we're talking about dark matter concentrations, which really can only be achieved if you believe in things like cold dark matter or in other theories, but you need to make it need to work a bit more. Moreover, the mean densities you observe are, on average, consistent with what you expect from this NFW profile for a halo of that threshold mass. That's the great thing there. Somewhere below, we can spend, so I have spent papers working on these things. So some things don't work out, some things work out better than others. But, you know, on the largest scale of things, it's not too bad, okay? Not too shabby is what my sons used to say when they were younger and not before Instagram and things like that. Not too bad, okay? So we want a smaller galaxy. How do we find them? Well, we use these big surveys that you guys, all many of you have been involved in. For example, of the Milky Way. This is, of course, the map from Gaia, view from map from Gaia. You see the Magellanic clouds here at the bottom, playing the galaxy. You see the little dots around there. Those are some of the galaxies that were in the previous plot. But let me find fainter things. And the way people do it is by looking at these things and finding overdensities of stars, and then looking in Gaia to see if those stars move together, first of all, and also if they are consistent with having, you know, a color magnitude diagram, as I say, you know, basically a relation between colors and magnitudes that are consistent with all of them being at the same distance from us. Give an example, local example. Here, local, well, look at me. A local example, I'm becoming an observer here. Right? This is from a recent paper, so recent it has not been submitted yet. So, by Julio and Saga from University of Barcelona, and a group which, for some lack of chance, it includes me here. And this is what you see. You find a cluster of stars in some survey. You look at them; they're all the same, you know, color-magnitude diagram, and then you see that in Gaia, at least the bright stars are moving together in proper motion. Okay? This particular example is even more local. Okay, this was discovered with flying stars, and of course Gaia. Those are the colors, the red and yellow stars here. But the blue stars actually from a deeper image taken from the Grand Tecan, which is somewhere around here, if my memory serves me right. Okay, this is no doubt this is a satellite of the Milky Way. Okay. This is a control field, just to give you an idea. This is how many stars you expect. This is how many you see. So there's no doubt about it. Now, what is it? Is it a galaxy or not? That's the trick now that we already encounter. We find lots of these things, perhaps not thousands, but many of these things, dozens, but we don't know what they are. And the way we say, well, if it has dark matter or evidence for dark matter, we call it a galaxy. And if it doesn't, we call it a cluster, a star cluster. As simple as that. I'm a simple man. I'm from Argentina, from the south. Simple men come from the south. I think Chris is here. Chris will tell it's true. Simple men come from the south. And that's it. So this is another one. This is the one I was telling you. Our esteemed galaxy hunter here from Victoria, Simon, who's visiting you here. From this one in the Unions survey. This is a different survey. And this is what it looks like. That's the color-magnitude diagram. This is what it looks like in the sky. That's the control. And the first thing you say is, well, really? Yeah, that's the first thing you say, what? I mean, what have you been drinking? No, drinking. What have you been doing? let's keep it there. And you go through statistics and you do Bayesian things and stuff that nobody really understands, but convinces a lot of smart people. And therefore you say, well, this must be right. There's something here, okay? Then you look in Gaia, but the real thing that convinces you is that you can take spectra. Because if you look at this thing here, there are a few stars above 20, 21. So few, but very few. It's because the only reason that we see this object is because it's so close to us. You see, it's so faint that it doesn't even have a star in the red giant branch. What kind of cluster is that, you say, first of all? It doesn't have a single star in the red giant branch. But it's very low mass, okay? Stars don't last a lot in the red giant branch, and therefore, it's low mass enough, you find ones that don't have it. So you only see the subgiant branch here. So Simon and colleagues went around, found measure spectra. Long story, it doesn't matter too much, but first of all, you can count the stars and come up with a correct for the stars you don't see, and we expect this system to have about 16 solar masses, right? And that's kind of a good estimate. 16, sorry, 1/6. It's crazy, right? It's not even a cluster. It's not even nothing. But why are we talking about this thing? Because interestingly enough, it is the faintest object that we've seen. Clearly, it is a satellite of the Milky Way. It's moving together. It's also the same distance, etc. This is in a plot that Simon made, comparing sizes versus magnitudes of known objects and faint objects. And you see that yellow thing at the bottom, that is what we call Ursa Major 3 or Unions 1, depending on whether you believe it's a galaxy or not. And I believe it's a galaxy. Why I believe it's a galaxy? Well, first of all, if it's a galaxy, the velocity dispersion should be such that you need dark matter to explain it. Because if it's a cluster, look at this. This is a virial mass, so velocity dispersion squared and size versus stellar mass. If it's a cluster, it's on this line, the bottom line here, where all the clusters are. That means that there's no dark matter, so velocity dispersion should be such that it's over there. But if it's a galaxy, it's on this other line or somewhere above this. Okay? And that's what we want to do, measure velocity dispersion. And Simon and collaborators, of course, did. And they kindly put me in the paper as last author, remember? So, but it doesn't matter. You always try to put your foot in the door somehow. And this is what you find, right? So you find a bunch of velocities which are not the same. You predict, if this is a star cluster, velocity dispersion is 50 meters per second. Meters. Okay? So it should be exactly the same velocity. And they're not. There's some spread. And that's when people start being nervous. So where is the spread coming from? Is it because of instrumental error, or the spectra has the line that's here not there, whatever? It gets complicated. To measure those dispersions of the order of kilometers per second, a few kilometers per second is difficult because, of course, the individual error per star is also the order of a kilometer per second or so. This seems very convincing to me, but many of my observational colleagues who have a lot more to lose than I do, they're younger, I think, and therefore they are more cautious. Say, well, look, if you take away the one on the left and two on the right, or one on the right, two on the left, whatever, velocity dispersion becomes consistent with zero. Okay? But as far as I've seen, even people who observe these kind of stars, still the velocity dispersion is about there, a couple of kilometers per second, right? Perhaps it's not, the jury is not completely out, but the jury is like half out, right? What convinced me of this is that you can actually, where the galaxy is. It's very close to us. So it's at, tens of kiloparsecs from the galactic center. And the Milky Way is very massive. It makes us go at 200 kilometers per second, right? It's really, really massive. And therefore has very strong tidal forces. If the thing is not dense enough, it will be ripped apart. Okay? We know its orbit, we know the velocity dispersion, its distance, velocity, its distance, etc. We know its orbit, we know its pericenter, its apocenter. If it has a cluster and we put it there without dark matter, it disappears before an orbit is completed. Okay? So basically, this must have dark matter of some sense. Some people argue, well, maybe it's an intermediate blast black hole, maybe it's a few of them, maybe it's a bunch of white dwarfs and neutron stars and stellar remnants and primordial black holes. Doesn't matter. Let me see what happens if I actually play the game that we saw before. Now we have a small galaxy, this 3 parsecs in size, right? So I can put it here. 3 parsecs, velocity dispersion, compute the mean density, and it's over there, 10 to the 10, big arrow bars. But it is completely consistent with being a cusp in the dark matter halo. This has a lot of implications. Let me see how many of them I'll go through. How much time do I have? 5, 10, 45 now. Okay, so I'll skip the dark matter interpretation here, a few slides. But I just want to leave you with this message. to zeroth order, this is basically the cusp or the remains of a cold dark matter halo that formed a few stars at the beginning and then orbited around, probably lost most of the dark matter halo at the outskirts, but the center remains. So I'll skip a few of these things on dark matter, and I'll tell you the other thing. But this is the faintest galaxy in the universe that we know. Okay, it was found by Simon. You should be saying, great. I mean, this is really important. I don't know. Am I getting too overexcited at my age, at my old age? Maybe. This does sound like my grandmother when she gets excited. It's not, I don't know. Anyway, let's look at this. What happens at this threshold? So I told you, we're at this threshold, and there are 9, we form stars, and we have the faintest galaxy, whatever. What happens to the left of this? To things that don't form any stars? How can we find them? Cold dark matter predicts that there should be many halos, but yet there still has not been a single convincing detection of a cold dark matter clump that doesn't have any stars. And there should be tons of them, thousands, hundreds of thousands of them. They're low mass, they're hard to detect, but they should be there. That is a prediction. So how can we test it? Well, below this mass, what happens is that what is happening really physically, why do we have this threshold? What is happening is that below this mass, the typical velocities of these halos are of order of less than 10 kilometers per second. At less than 10 kilometers per second, when atoms of gas collide, hydrogen collides, neutral hydrogen collides, the velocity of the collision is not enough to excite Lyman alpha. You can excite Lyman alpha, you can emit energy. You don't emit energy, the gas remains in hydrostatic equilibrium in the halo. It doesn't collapse to the center. It needs to emit energy. So that's the simplest interpretation for this threshold. You are in the regime of very low mass, very, very low velocities, and therefore collision. So you can actually simulate this. There's no stars, there's no feedback, all those things that people play around and have lots of bunnies that come out of a hat. And you can predict what they are. There should be something like this. A dark matter halo has a little clump of gas. The gas is in hydrostatic equilibrium at the center. And in the most massive ones, it should be massive enough to form H1 at the center. So you couldn't precisely detect these things, the little core of H1 at the center. The rest is ionized by the UV background. Okay, so where do we expect them to be? This is in the simulation of the local group. You expect them to be far away, because if they're closer to any big galaxy, close enough, they will get run pressure stripped. You see, gas is easy to strip away. And therefore, you should find them in isolation, far away from galaxies. There are not very many of them. You can see here, these are the ones that lost their gas, the middle. These ones that didn't lose their gas on the left. There's still a few. They're few, they're hard to find, and this H1 core is only visible in the most massive of them all. So there are not very many of this. So you don't expect them to find them everywhere you open up your H1 or your radio telescope, okay? But, they should be there. They should be there, and we made predictions, make sure the sizes, etc. I'll spare you the details. Let's go to what we actually found. I'm not in this paper because they didn't do anything for it, of course. So in this case, it's not like, and I don't have friends like Simon. This is from the FAST telescope, the Chinese telescope, actually is the biggest radio telescope in the world. And in a survey of M94, one of these close by, like M81, M94, CN8, these big galaxies around the Milky Way, about 3 or 4 megaparsecs. This is a spiral galaxy, it's interacting with another one, whatever. The macro is in H1, and they found a bunch of clouds, and in particular found this one, cloud 9, which if you're of a hippie extraction, cloud 9 seems good, is that right? Where you go to cloud 9 is where you go if you do things that are not permitted on YouTube, so therefore we're not going to do that. But anyway, cloud 9 is in a little box, and it's actually far away. It's over here, or here. It's far away, and it looks like it has the same size, it has the H1 content, and it has more or less the structure that we expect for a cloud of gas that is supported by its own dark matter halo. How do we test this? And it looks good, it looks kind of roundish, it looks like it could be that. That's the right size. With another characteristic of this is that gas is in hydrostatic equilibrium. So the line profile in H1 that you should see is the line profile of a thermal, motion at 10 to the 4 Kelvin, which is about 10 kilometers per second. Okay, and this is what the lamp profile looks like. Looks kind of Gaussian, and it has the right width. It's a bit bigger than we wanted, but nature is like that. You want 12 and it gives you 15. You say, well, what do you do with that? Close enough. We observe this with a GBT, same thing. You observe this with a VLA. This is what it looks like. The VLA looks a little bit distorted, as if it's interacting with something that complicates a little, but it doesn't change too much. These are line profiles from different telescopes. They're kind of different, but the difference can be expected because different telescopes, of course, some are more sensitive to smaller scales or larger scales, etc. Lots of details. All I want to say, this is consistent with this clouds of gas that don't have any stars in halos that are below the threshold. We call them relics, for reionization limited H1 clouds. Relics. Pretty good, huh? Actually, I came up with that acronym, and nobody repeats it. I don't know why. I think it's great. Anyway, but so what do we do? Now we need to convince ourselves that it doesn't have stars. So we apply for HST, and this is the first image we got from HST. We have an example of a cloud that's very similar to us, which is much closer to us. You see, this is 4 megaparsecs from us, near M94. We have another one, which is called Leo T. Leo T is a galaxy discovered by H1, then confirmed to have about 10 to the 5 solar masses in stars. That's what Leo T looks like to scale, right? If I take it and put it at 4 megaparsecs just in size. And so that's where it should be. That's the VLA centroid, and that's where it should be. This is the first image from HST that we got. Then, of course, we got more orbits. We got 8 orbits on it. That's the ACS footprint on the VLA contour map. And this is what the picture looks like. I mean, the projector always hides a bit of things, but you should see here, if we had a 10 to the 5 solar mass like Leo T, would easily see it, but really easily. There should be dozens or 100 maybe the stars that we'll see in the red giant branch. 10 to the 4.5, also 10 to the 4.2, 10 to the 3.5, it's the massive glacier. It's the only way to see 2 or 3 stars. And that's kind of where you end. So this really is a galaxy that has less than 1,000 solar masses in stars because there is nothing else there. Just to see how extraordinary this object is, let's compare the Leo T. And let's compare the other galaxies of similar H1. Okay, so this is now mass in stars on the x-axis and mass in H1 on the y-axis. That is, the typical thing is, there's the H1 to stars about 10. These are selected to have H1, so that's why the numbers are pretty big. This is the alfalfa survey. And you see, the alfalfa survey says, when you have 10 to the 6 or 10 to the 6, 10 to the 7, you expect to have stars of 10 to the 6 or so. There are not very many of these objects, of course, very hard to find. But that line is less than 3.5 or whatever to the left. Compare that with Leo T and all the other ones. These fashy dwarfs are the ones that FAST has been finding in the local universe. And they are, of course, also H1. That's how they detect them. But every time you see H1 of this amount, like 10 to the 6, 10 to the 7, you always see a galaxy. And the galaxy is usually pretty big. You find it a posteriori because the sky is big, but it's always there. But not here. So this is really an extraordinary object that, of course, begs for more observation. So this has been just submitted to somewhere, whatever, actual letters or something like that. We don't have money to pay for any of these things. So I guess it's not only you who suffer from money, but that's where I leave you with the story. I told you about the faintest galaxy in the universe, and then I told you about something that's even fainter than that. This has no stars that we can find. Okay, so leave you my summary, and I'll, of course, thank you.
Thank you, Julio. Questions? Carlos.
Thank you, Julio. Very, very nice talk. Just let me switch off my cell phone, which is just in time. You start with me now. Okay. Just a couple of questions. So this is a firm prediction from Cold Dark Matter, right? Lambda CDM, that you have this population of small subhalos dominated by dark matter that either produce very few stars or just retain some pockets of hydrogen, neutral hydrogen, and that's it, right? What is the fraction, have you go for a Milky Way type of halo? What is the fraction of dark matter that would be contained in these small mass subhalos? Do you know?
The fraction of dark matter in the Milky Way halo, you mean, that's contained in small clumps?
Yes.
Well, we don't know that for a fact, but the prediction from cold dark matter is that it's of the order of 5%.
5%.
Yeah, a few percent, a couple of percent.
All right.
Basically, all the mass, if you're interested in total amount of mass, all the mass is in the most massive object. You tell me one most massive object, and I'll tell you what the mass is. Because if you add all the other ones, it doesn't add up much. In the case of Milky Way, most of the dark matter, I guess, in clumps is in the LMC.
Right.
So it's about 1 in 5, 1 in 10.
Okay. And one more question. The prediction on H1, to what extent does it depend on the details of reionization physics? The fact that they are able to retain some neutral hydrogen that does not get ionized, destroyed by the UV radiation, does it depend a lot on the recipes that you put on reionization or not really?
Well, there are no recipes here. We observe the UV background, at least a low redshift. So actually, we have a very good idea what this looks like. The assumptions come in, when you look at the structure of the gas there. So, for example, the gas gets very dense. You may have other things like formation of molecular hydrogen, other phases that you don't see, etc. But at the regime of the densities that I was showing you here, at least the models that we've done, its physics is just very simple because it's just recombination and ionization. And all you have is a density profile given by the pressure equilibrium. But this is local, so this is here. This is just next to us. So actually, we do know fairly well what is the UV background. Oh, reionization over there in the early. Yeah, but we're not using any of that. So this is an observation.
Hydrogen will be reionized with the reionization. Only few pockets will be made.
No. In these objects that don't have any stars, okay, all the halos should have the same, before reionization, all the halos should have the same amount of gas to dark matter. Reionization comes, heats up the gas at the ionization energy of hydrogen, 10 kilograms per second, 3.6 eV, whatever, 13.6 eV, right? So anything that has less to 13.6 eV, basically will be, sorry, if the halo has energies less, or masses that correspond to velocities less than that, the gas is too hot. The gas will flow out of the cell. And the local quantity will start going down. In halos exactly at the threshold, the amount of gas that flows is less important. Okay, still a lot remains, and it forms that clump. And if you go a bit more massive, that particular, center becomes dense enough to produce H1. Now, I'll show you a plot of this thing. This plot this is, the solutions for different relics of different halo masses, different colors. If you go to, and this is the total amount of gas density, and this is the gas density in H1. And you can see here that you need halos of, say, that are red, 10 to the 9 and a bit, or to have any H1 in the center. Okay, so make those solutions powerful.
Hi, Julio. Thanks for a very nice talk. I guess just a little bit, one is more of a comment and one is a question. The comment is that people have been trying to look for these dark galaxies for ages. So a few years ago, if you speak with alpha surveys people, they will say that they have identified all these H1 clouds. But then later on, with the discovery of ultra diffuse galaxy, they could actually find also a stellar diffuse counterpart. So I think that the nice thing now is that we're going to much lower scales of stars. So we're not talking anymore about 10 to the 7 to 10 to the 8 stellar masses galaxy, but much smaller objects. And I think, so yeah. And I think it's, we can make prediction about how many of these objects we should find in the local group, and we should possibly find it with a fast survey. So if you have any feeling of how many of these H1 clouds, which are not ultra diffuse galaxy, but truly relics, we should be able to get in local group environments?
Not very many. That's the bottom line. This is the plot that convinced me, at least. These are the dark matter halos that massive enough, some each one, but have none, or no gas whatsoever. That's because the gas has all been ground pressure stripped. So if you're actually close to the galaxy, like in the local group, there's too much gas in the intergalactic medium, intersynchron galactic, I don't know, there's so many names in place, CXM, CGM, whatever. In the medium of gas, there's too much gas, and the things move around and they lose it. The gas is it's very weakly bound. Right? So you want these things to retain gas, they have to be outside. So if a local survey like alpha high velocity clouds, for those of you who know what we're talking about, but the problem it has is a lot of those things have velocities which correspond to objects in the galaxy or very close to our galaxy. And that's why I don't think they are this object. They're not, I mean, they're interesting objects, but they're not this. They're not, they have to be far away. And Cloud 9 in M94 is, as I said, it's about 80 kiloparsecs in projection, it could be farther from the galaxy. So it passes all those sanity checks, but we still need to study more, of course.
And sorry if I can keep on this side. How strong is your prediction against different model for physics that you put into a simulation?
Changing dark matter, you mean, or changing?
No, it's more about changing the physics.
The voice of God is coming there, I see it. It happens. Every time I say self-interacting dark matter, something will happen. So it's called invoking the gods. Right? I mean, the only physics that go here, since there are no stars, there's no feedback, none of the stuff. It's very, very simple. The only physics that goes in here is what is the thermodynamics, thermodynamics, of gas at these low densities. And this is a relatively fairly robust result. And this is basically the density of gas and its temperature. If it's, if you shine UV background onto it, with the typical UV background spectrum that one would observe. Okay? So you shine gas and you have this equation of state, as you want to know, the relation between density and temperature. And you have two branches, this T heat equal TH, which is where you heat gas by making them collide with photons, and you reach equilibrium, or not equilibrium, you reach a temperature given by the age of the universe. You put the gas and heat it enough, you'll be hot, but it's only 13 billion years, you get to that branch. The other branch is where the heating timescale equals the cooling timescale. You get hit once and you cool once because you're dense enough, you now can cool by exciting radiation. And therefore you have these predictions. But you see, it's not, although it looks complicated in detail, if you look at it from far away, like from the back there, you'll see the scales here. This is 4 to 4.5. This is a factor of 2 or 3 in temperature. It's not a big deal. Okay, so provided the physics is not crazy, like if we live in super bubbles that are being heated by galactic cosmic strings and energy coming out of nowhere, or phantom energy from dark energy, who knows? Of course, one can make things very complicated, but it's very, very independent of all the details that one, is usually different of when we talk about simulations of galaxy formation, because there are no galaxies. So that's the saving grace. Yeah. I think that will change how many there are, but it won't change the structures today, right? So, yeah.
Julio, thanks for your talk. Very nice. I was wondering whether we could be observing a potential bias from the observational point of view, and therefore an overinterpretation on the shape of the profile, Caspi or not, when selecting targets just based on a few number of stars, as you have shown, no? Because to be able to detect those objects, you need to see them somehow clustered, right? So imagine that you were having them less clustered, they would not pass some threshold of detection, and therefore you would be missing a potential population of very dispersed, very diffuse galaxies that then could be compatible with living in core dark matter halos, for example. And so I'm a little bit worried, a little bit worried that this could be happening, no? Because definitely we are biased towards the denser galaxies.
Yeah, no, I'm of course very aware of the pitfalls of different selection effects and things. And if the data change, I will change my mind. I have no problem. This is the data we have today. This is all the galaxies, all the faint galaxies we have for which this measurement can be made. And so, you know, you can draw different conclusions. People draw different conclusions. You look at this for an SIDM perspective and say, oh, well, no, all that's happened is the SIDM cross-section that used to be 0.1 centimeters per square per gram is now 400. If I change that, then I have core collapse, and I have all sorts of different things. And you can explain this, which I think is fine, right? I mean, it's an explanation. Which one is the correct one? I'm not sure. But I agree with you. For example, if it's SIDM, to say something, and it's because you get these dense objects because this is core collapse, there should be others that are not core collapsed. And therefore, there should be many, or at least one or some numbers that are small and they're low density, 10 to the 7. Those don't exist yet. Don't they exist because we haven't found them yet? Or because they're not there? We can speculate all we want, but you know, you're an observer. You're supposed to go and find them and give it to us, and then we will change our minds and we come up with another more complicated model. But so far, I see no clear and obvious and urgent need to change, you know, the standard cold dark matter paradigm based on this line of arguments.
Any other question? Last question then.
So thanks for the fantastic talk. It's more a comment than a question. It's about these other models that are alternative to cold dark matter. You kind of argue that the density that you expect in these models is going to be the same for all of them. Okay, and I mean, I'm not completely clear that that's the situation, because if you form the cores, I mean, all these models redistribute the matter and form in an inner core in the dark matter hell. So if you kind of come from NFW profiles, you inherit the properties of the profile. And so the small halos, I mean, if you form a small core, you have a core of high density, even in these other models, alternative to cold dark matter. We can talk to these things later on if you wish. Okay. Yep. So I'm not completely sure that you expect a constant density in all the alternative to cold dark matter. It's actually the other way around. You expect a density that increases as your core is smaller.
Let me just clarify. When I say expect the same density, it is because I motivated the fact that all of these dwarf galaxies should live in halos of the same mass. If I have halos of the same mass and have the same physics, collisions or between elastic collisions between particles, then all the halos of that mass should have the same core, because they all have the same structure and they have the same number of collisions per unit time. And what I think you're saying is that if I change the halo mass, I can get cores that are different densities, and I think that's true. If halos, all these galaxies live in the same halo.
If you change the core radius, so for some mechanism, not all of them produce the same core radius, then the density is gonna.
No, the core radius here comes from a very well-defined physical mechanism. There's the number of interactions, the collisions that you have per unit time. The core appears, you see the red, the blue line appears where the number of crossing times, the rate of crossing times equals the Hubble rate. In other words, when you have one collision per Hubble time, or X number of collisions per Hubble time, and therefore should be all the same if you don't change the halo mass.
Okay.
Okay, we are a bit over time, so let's stop here. And Julio is sitting in one office in the first corridor, top floor, right? So if you want to find him and talk to him later, he will be around.
Thank you.
Thank you very much.
Sí. Pues no hay aire aquí. No hay aire acondicionado. ¿Sí?